first talk a bit about Tesco. Now, Tesco is a #1 UK grocery retailer and is among top 10 in the world. Tesco has more than 330,000 employees across the geographies working together in order to deliver and serve our customers daily. Now, I would want to try to visualize what is transport. Now, let's say one fine morning you went to a nearby grocery store to pick up some products like pizzas, chocolates, or bread, or better yet, got it delivered through your online delivery app. But behind this simplicity and readily available products lies an intricate orchestration of transport, logistics, and planning that works all in harmony to deliver these products to the end customers. Now, generally, this journey of the product starts from the suppliers to the depot, known as the primary transport. From the depot, it goes to all the stores, which is known as the secondary transport. From this is now goes to the end customers, which is known as the last mile transport. Now let's dive deep into secondary transport with me. I am Vipin, working as the software engineer at Tesco, and my today's topic is revolutionizing secondary transport, transforming VRP with metaheuristics. Now let's suppose you get teleported to one of our Tesco depots, and one of our depot manager comes in and asks you to plan efficient routes to all the stores in order to deliver the goods. Now, when you get this problem, what will you think? What is efficiency of a route? How will you plan an efficient route? The efficiency of the route can be to reduce the cost, anything that is related to the operations, right? It could be fuel, anything that will reduce the operation cost. Now, this is called the basic VRP problem. It is to find the efficient routes in order to deliver the goods to all the stores. Now, the first order comes in. Let's say the first order has to be delivered to 3 stores. Now, the number of combinations that will be there for the 3 stores will be only 3 route combinations. So even manually, within minutes, you can plot the routes and find out the best solution and give it to our depot manager. But the next comes in order for 10 stores. Now suddenly the number of combinations explodes to more than 2.5 million combinations. Now it won't be possible for you to deliver the product, to find the efficient best solution in order to deliver the goods to the stores manually. So what you do, as most of us here are software engineers, probably would go and write one very nice brute force code in order to scan through all the route combinations in order to generate the best solution. And after writing the code, you get the solution even within seconds or minutes, depending on your machine capability. But the next comes in orders for 20 stores, and you started your brute force code. But now this time, it is taking 1 hour, 2 hours, even 3 hours, and you are sitting there and hoping that your code will stop running. But in fact, you will need to wait for another 77,000 years in order to get to the best solution. And if the order would have been for 60 stores, it would have taken the universe in order to get to the best solution. Now, as you can see, the scale at which the vehicle routing problem operates. So basic routing problem size increases tutorially. Now the output depot manager comes in and asks you, no, you don't have to just plan efficient routes, but also you need to take care of if the vehicle gets overloaded or not. You have to take care of the capacity of the vehicle. And also you have to plan the trailer space efficiently. You can not send trailer half empty. This adds another layer to the basic vehicle problem, which is known as capacitated vehicle routing problem and bin packing problem. Now again, the depot manager comes in and adds another sub-problem to this problem. He tells you, no, you cannot use static drive time in order to route all the trailers. The drive time will change according to as per the traffic at that particular situation. So now there is another sub problem called stochastic vehicle routing problem added to on top of the basic routing problem. It is about now you have to plan the departures of the trailer according to the drive time, and to make it efficient, you really need to plan according to the drive time, according to the traffic, so that you can efficiently deliver the goods. Now, again, the depot manager comes in and says, no, in the plan, you also need to make sure your products are getting the correct time slots to the stores. You cannot deliver the products out of those time slots. Now, this adds another complexity to the basic vehicle routing problem, which is vehicle routing problem with time windows. As you can see that as we keep on adding the sub problems to the basic routing problem, which in itself is a very complex problem to solve, the problem is keep getting complex and complex and complex. Just by adding 3 constraints, as you can see, the problem has get so much complex. And in real world, we solve more than 40 constraints or 50 constraints the depot sends us in order to deliver these products. And we at Tesco Transport Technology makes this possible by handling all these interconnected constraints and plan an efficient routes in order to deliver these products to our end customers. We at Tesco operates at very high scale. We have 28 depots in UK, which serves more than 3,800 stores. We travel around 3.5 million miles in UK, which is like traveling to moon and back 7 times. And we handle more than 40 constraints in the routing plan at once in order to deliver the products efficiently. Now, after understanding what is vehicle routing problem in real world and how complex it can become, let me formally define what is vehicle routing problem. Vehicle routing problem is a combinatorial optimization problem where we have to find a set of efficient routes in order to deliver the goods to the end customers with a given set of vehicles. You can see this graph, right? This is the number of routes that you need to deliver to 30 stores. This is with 500 stores. You need to make sure that each and every route at the depot operates efficiently. Even if one of the store pairings or the number of the stores which are going here in these routes is not correct, depot won't accept your solution and they will not operate on that. So this is how complex the vehicle routing can get. Now, how do you solve it? There are 2 methods defined in literature. One is exact methods and one is heuristic methods. In exact methods, it is guaranteed to find the optimal solution. When I say optimal solution, it is the best possible solution that you can get, and there is no better solution in that solution search space. So you might ask, why do we have another method, heuristic methods? If we have exact methods, we can guarantee us the optimality. But the problem comes when the problem size increases. With the problem size increase, the exact methods become less efficient. Even with 100 stores, with more than 100 stores, you cannot get a good schedule or the plan within a reasonable time. Within a definite problem size, it is a good thing to use exact methods. But after a certain problem size, we cannot use it. There are many algorithms that is part of exact methods, like mixing linear programming, branch and cut, dynamic programming, and many more. Now coming to heuristics. Heuristics are the approximate methods which are used to find, which gets us a very good high quality solution within a reasonable time for a very large problem size. Even you can solve problems with even more than 5,000 stores within a reasonable time in order to deliver it to the stores. Now, in heuristics, there are many meta-heuristics that are in literature and many more. It has been the most researched topic since past 20-30 years, meta-heuristics. And you can get n number of ways to solve the problem. One of the few of them are local search, taboo search, simulated annealing, and colony optimization. In today's session, I will mostly concentrate on local search. Local search is an optimization technique used to which what it does, it refines the solution iteratively by improving the solution. It iteratively improves upon the solution. Now I've been talking about solution. So what is a solution? Solution is the desired outcome of the problem which follows all the constraints. Now in context of vehicle routing problem, it is the set of routes which can deliver to all the stores by following all the constraints. Now get a bit more into local search and what is this iterative search. There are different phases involved in local search, and the first phase is initial constructor. In initial constructor, what we do is we try to find the first solution that will start this iterative search. Now this first solution needs to be feasible. Now feasibility means it cannot violate any of the constraints of the problem, so it should be feasible, but it doesn't necessarily need to be a good or optimal one. Once you get this initial solution, you go through to another phase, that is the neighborhood search. In neighborhood search, we try to do a small change in the solution in order to get to the next solution. Now this next solution, this set of solutions that we can get by applying a small change in the solution is known as the neighbor. Now for example, right? Suppose you have two routes, and in two routes there are multiple stores that you are delivering. Now you swap two stores between the two routes. Now this becomes a move. Now imagine when you swap the stores between the two routes, you will get two new routes, right? Now this will become our new solution. So that will become the neighborhood of the solution. Now, or the candidate solution. Once we get the candidate solution, we go through constraint checks. Now constraint check makes it possible to see the feasibility of the solution. We have to make sure that all the constraints of the problem are followed whenever we find out a candidate solution. Now, for example, right now we did the swap between the two trips, right? By swapping the stores between the trips, it might have happened that the vehicle capacity is exceeded because the different store could have a different demand. So vehicle capacity could exceed and violate the vehicle capacity. So it will become infeasible. Now when it becomes infeasible, we call the neighborhood again, and then it again applies a move to find another candidate solution. And this cycle goes on until we find a feasible solution. And once the feasible solution is generated, we evaluate the fitness of the solution. By fitness meaning the cost of the solution. For example, for vehicle routing problem, it could be the of distance traveled by all the routes in the solution. Once we evaluate the cost of the candidate solution, we get to acceptance strategy. Now, in acceptance strategy stage, what happens is its job is to accept the candidate solution or to reject the candidate solution based on the cost calculated. It is the way to guide the solution through such phase in order to get to the best solutions. Now, if it rejects the candidate solution, it will go to the previous, it will maintain the previous solution. If it accepts the candidate solution, the current solution will become the candidate solution, and then we reach to the stopping criteria. Now, stopping criteria here is important to break out of this cycle and of the optimization cycle. And it can be based on time or some other complex heuristics depending on the problem. Once the stopping criteria, suppose the stopping criteria is not met, we continue to the neighborhood search and again try to find the new candidate solution, and this cycle goes on until the stopping criteria is met. At the end of the cycle, whatever is the best solution is accepted as the solution. Now, I'll talk a bit about local search, some terminologies like how the solution search space can look like. Now, suppose this is the y-axis, this is the y-axis, and this is the x-axis. The y-axis represents the cost of the solution, and the x-axis represents the number of solutions that can we get in different iterations. And this whole becomes the solution search space. Now, imagine this is a landscape of mountain and valleys. There are peaks, these are the mountains, and these are the valleys where we can go. Now, the peaks represent the worst solutions, and this values represents the good solution or better solutions. So what iterative or local search or searching through this landscape means is you need to hike through these mountains, go down to the valley. Again, and there could be another valleys with better solution. Each valley represents a good solution, but there could be multiple valleys. In this, as you can see, there are two valleys. This one has a better solution than this one. The deeper the valley, the better the solution. Now, we will traverse through the solution search space. Suppose in the initial constructor, we got a solution with a distance cost of 9. Now what you do in the next phase, you apply a move. Once applying a move, it can happen that you get a better solution. You accept it using the acceptance strategy. Once you start accepting, now you apply another move. Suppose it doesn't have a good cost, and then you reject it. Now, whenever you get a good cost or better cost than the previous solution, you start accepting it. Now, when you start accepting it, what happens is you will then get into the first local optima. Local optima can be obtained easily just by accepting the improving solution. But the problem comes when we have to escape this local optima. What we have to do? We have to reach this point, right? How do you think we can reach this point? There are multiple ways in literature defined in order to get to this optima. One of the ways is to accept a worsening move. Now, what is worsening move? Worsening move is such, by doing a worsening move, it means that we are accepting a solution with a higher cost in order to climb the top of this mountain. Now, we keep on accepting this worsening move, we keep on climbing the mountain, and there could become a stage where we start accepting the solution with lower cost. Now, the acceptance strategy changes in order to now accept the lower cost solutions, and finally, we can reach the second local optima, which is with a distance 5.8. So as you can see, in meta-heuristics, it is all about finding the best solution, best values. We can get the best solutions. And in actual VRP problems, in the real world problem, this is how this solution search space looks like. There are millions and millions of values, and you have to traverse through this search space in order to get to best local optima. The best one is called the global optima, but we never know what is the global optima because we never know. It is not possible to search through all this valleys and mountains. So we find the most optimal solution that is possible to get within a reasonable time and deliver it to our depots. Now I have prepared a demo for. So it is about a variant of vehicle routing problem called capacitated vehicle routing problem. So as you already know, this the vehicle routing problem is a combinatorial optimization problem. But in this, what we do, we have n stores each with a known demand. Always a route starts from a depot, goes to different stores and deliver the product, and then come back to a depot. And we have unlimited vehicles, and each vehicle has a fixed capacity. And the objective of this is to reduce to the total distance by finding the set of routes. And in the input, we get the coordinates of each store, demands for each store, and the vehicle capacity. And the constraint is there is only one constraint where the total demand served by a vehicle does not exceed its capacity. Now, this is the starting point, right? This is from the initial solution. Suppose this is the initial solution, and the iterative local search is starting. Now, as you can see, the solution cost is decreasing and the different routes are now getting created. All solutions that you are getting are the candidate solutions for which we are accepting the solutions with lower cost. And as the local search goes on, the solution cost keeps on decreasing and decreasing because we are accepting a better solution. Now for this experiment or the demo, I have used a ruin and recreate method, where in ruin method we remove some of the stores from the trip, and the removed stores are then recreated or inserted in the new routes. This is a move which is called a ruin and recreate method, and the acceptance strategy is used is late acceptance hill climbing strategy, which actually accept the worsening moves to escape the local minima. Stopping criteria is time, and the problem instance has 80 stores with vehicle capacity 100. I want to show you this graph. This is the state of the initial solution, which has the number of trips as 11. These are the 80 stores, and the best solution has this graph with number of trips as now 10. You can see, right, how jumbled up this routes looks like. It doesn't look pretty at all. There are so many overlapping routes and so many long routes. After finding out the best solution, you can see how the best solution looks like. It's more organized and better trips are present. Even it is able to decrease the number of trips. So the distance decreased from 2429 to 1799. And we got this solution just within few seconds. It would have taken millions and millions of years in order to do this with some other methods. But with heuristics, we can achieve this within just few seconds. Now, I want to conclude my presentation by giving some results and savings at our test go. So with our solution, we were able to, until now, we have been able to transport more than 66 million products and units of products. We have been able to, in comparison to the third-party solution we were using before, we have been able to reduce number of miles by 140,000 miles per week. CO2 reduction is 165 tons per week, and we generate all the legally compliant schedule. Here, solution had a lot of manual planning involved. They had to change the planning in the depot in order to actually execute. We give 100% executable schedule to the depots, and we have our own routing platform. Thank you for listening to my presentation.